This last section of chapter 6 talks about a specific subset of random variables, binomial random variables, which is what I'm going to be talking about in this one, and then a little bit more about those and geometric random variables in the next one. We're going to be focusing in this one on binomial random variables, how you can recognize them, and then how we calculate the probabilities. When you look at a statistical situation that it's asking for the outcomes of a random chance situation, you want to pay attention to see if that situation meets these requirements. And if so, then you're going to do your calculations in a particular way. So a binomial setting, there are 4 things that need to occur. One is it binary? That means that the outcomes of the trials, even though there might be 8 different things that can happen, you're going to be able to split them up into a success or a failure. And normally paying attention to a specific number of times something happens. Are the trials independent of one another? Do you know ahead of time going into it the number of trials or repetitions that are being expected? And then do you know that the probability of what a success is, and it's the same probability every time? Let's give an example that we've had in class. We collected data on, and then we'll continue to look at tossing 3 coins 20 times. So we know that each toss is independent of the tosses before it. And we're going to define our variable as 2 heads being a success. And we find out that then we also know the probability of that success is 3/8 chance. So we've met all the requirements. It is binary. You either get 2 heads or you don't. Each of the tosses is independent. We have a fixed number of trials, and then we know the probability. So this is an example of a binomial random variable. Then from there we can start looking at specific values of x. We had 20 trials, but we might be interested, for example, in what's the probability that you could have 8 of those 20 have 2 heads. And that's the kind of question that we might be looking at. So just to clarify, there's a couple of things. That binomial random variable, once again, is counting successes. A distribution is the probability distribution of this kind of thing. It's going to look the same way with a table or with a graph, same way as a normal or another kind of probability distribution. Key issue is number of trials is known ahead of time. The probability of the success is the same every time, and you know what it is, and the possible values of x from 0 to n. So let's use our example of the number of times you got 2 heads in the 20 tosses. If we're paying attention to specifically to the number of times we got 8 out of the 20, then the probability of random variable x would be 8. If we wanted to know none of them, then the probability of random variable x, binomial random variable x, would be 0. All of them, x would be 20. So when it says the possible values, that means it could be anything from 0 to the total number of your trials. So we're going to look at a specific situation, and the minute you see a probability situation, you want to kind of run yourself through the acronym that will help you figure this out. So each child in this case is a particular pair of parents that there's a probability of 25% that they have type O blood. Genetics says that children receive genes independently, and the parents have 5 children. So we're going to look at the count X of children with type O blood. This is a binomial random variable because we are defining a success as having type O blood, and a failure then would be not having type O blood. Genetics says it's independent. We know the fixed number going into it, which is 5, and we know the probability, which is 0.25. So if we're going to find the probability that exactly 2 of their kids are going to have type O blood, we are going to look at all 5 of the kids, right? And we want 2 of them to have type O blood, so there's a 25% chance and then the other one would have 75% chance of occurring, 75%, 75%. So here is one possibility. They have a success, a failure, a failure, a failure. First two kids are zeros, type O's, I mean, and the other one. So we could write that also with exponents. Here's the two that are a success, and here are the two that are considered a failure. Not really, because they have type 0 blood, but you know what I mean. There's more to it, though, when there's a binomial probability, because the way I set this up is only one of the possibilities of when the kids are born. The first two could be type O, and then the other ones wouldn't. There's more arrangements. So here we have the arrangement that I set up. The first two kids have type O, and then the last three kids don't. Here's the probability, and then here's the probability of the failures, and we go ahead and calculate it out. And we get the probability of this one arrangement occurring is that, well, there are more than one arrangement that could work. For some reason things are weird with the video tonight, I'm sorry. On the last screen I showed you the two first kids having the type O, and then the last three. That's one way that the kids could have been born in that order. And that's also this one, for example. What if the first two kids did not have type O, and the third did, fourth did, and fifth did? There's a total of 10 ways that the children could be born and still have two kids have type O blood. And so you would take the original calculation of the probability of the two that do have it and the three that don't have it, and then you're going to have to multiply that by what's called the binomial coefficient. The 10 different ways, the arrangements, the total number of arrangements that you could have for that particular situation. So the binomial coefficient, the total number of arrangements in this particular situation with the 5 children, it's not that difficult with an organized list to come up with all the possible combinations or ways that it could work. But that's not necessarily a efficient or feasible way of handling it. So the binomial coefficient, the number of coefficients, the number of arrangements, I apologize, that are possible, it's fairly easy to calculate, even though this looks pretty whack-doodle. So we had five kids, and we wanted to know all the combinations with 2 kids. This is read as 5 take 2. And the way it works, and you've seen this before, depending on which math classes you got up to, 5 factorial, which means 5 times 4 times 3 times 2 times 1. And then K is, in this case, we want 2 kids to get that O positive. And then N minus K, so 5 minus 2 would be 3 factorial. I'm going to do this one by hand. You can go ahead and write it out and cancel it out, but we'll learn how to do it in a calculator as well. And so here we can have, like, this 2 can cancel out that 2, that 3 can cancel out that 3, and I'm missing a 2, so this 2 can cancel out, and you end up with 5 times 2 up top, which was the total number we got here. So you can calculate the number, you can find that binomial coefficient without having to make an order. So to find the total probability, you're going to need this binomial coefficient, and then we're going to multiply it times the probability of a success as many times as we want. In this case, we're talking about 2. So we'd have the 10, probability of success is 0.25 twice, and then the probability of a failure would be 1 minus the probability of success, which is 75%, and then N minus K would be 3. And that's how we would calculate the probability that we have 2 kids with a probability of 25% and 3 kids, the probability of 75%, and there's 10 ways of that happening, and then we calculate it. A couple of quick things if the symbolization gets confusing to you. First off, K can be any number we can choose from 0 to N. In our case, we were talking about K being 2, but we could also talk about K being 3, which is 3 children, and 4 being 4 children, and 5 being 5 children in this case. Factorial means that number times 1 less than that number, whoops, that's not 1 less, times 1 less than that number, times 1 less than that, all the way down to 1. 0 factorial is defined as 1, as well as I might remind you that something to the 0 power is also 1. So to put it all together, we have K meaning the number of successes you're looking for, and ending the number of trials. You're going to go ahead and find the number of arrangements, and that's n take K, and do the factorial components, and then you're going to take the probability of K happening. When you recognize that you have a binomial probability on the test, you want to make sure that you communicate that you notice that it is a binomial distribution, that you need to communicate the parameters of the number of trials, the success probability, and the values of the variable, specifically what you're looking for. You're looking for x equals 3, you're looking for x equals 4. Show all your work, and either show your work by plugging it into the formula after you've defined them, or I'm going to teach you later how to use the calculator command. But you always want to communicate in more of a paragraph form, or sentence form, the numbers of interest in the fact that you recognize that it was a binomial distribution. Here's a situation from a couple of slides back where we were looking once again at that family and what's the probability now of 3 kids having type O blood. And so here you see that stated right here. What's the probability that the total number of successes will be 3 out of 5? And there we get it right there, 5 take 3. And we would write that, if we were writing it out, we'd write 5 factorial over 3 factorial, and then it's 5 minus 3, 2 factorial. It works out when you cancel that out to be 10. So it would be 10, there's 10 ways, times the probability that you're going to have type O for those 3 kids, and the probability that they won't have type O for the other 2 kids, and you end up with about an 8.7% chance that 3 of the kids will get type O blood. Adding on to this, let me make sure that it doesn't come through properly. I don't know why. So if we wanted to check in to see if more than 3 kids having type O blood, what's the probability of that? Should they be surprised if more than 3 of their kids have it? We would then look at just the probabilities of x equals 4 and x equals 5. So we'd have 5 take 4, and then here's the chance that you get it 4 times. Here's the chance you don't get it 1 time. And we're going to add it to 5 given 5, which is just 1. And then here's all 5 getting it and all no kids not getting it. And remember, this would be just a 1. So here's the probability of 4, and here's the probability of 5. We add it all together. And then you have to answer the question. And the question in this case is, should parents be surprised if more than 3 of their children have type O blood? Well, here's the percentage, 1.5%. And since 1.5% is so low, then if more than 3 of their children had type O blood, their parents should be surprised.